Welcome to Naradar Academy. In this video, just I am going to give you a comparative study of interior point, limit point and adherent point in the real line. Okay, so this is a comparison. Okay, see, first let's see the definition for interior point. A point P in R, that is a real number, is said to be an interior point of a set S if there exists an epsilon greater than 0 such that P minus epsilon to P plus epsilon is completely contained in S. Okay, so for a point to be an interior point, there must exist at least one neighborhood which completely lies within S. Okay, right? So at least one, there exists an epsilon greater than 0 means at least for one epsilon, this is a neighborhood. No, the neighborhood P minus epsilon to P plus epsilon is completely contained in S. See, whenever you take a real number, for that number you can have infinitely many neighborhoods. Okay, but at least one of the neighborhoods should completely lie within S, then that point is called interior point. Okay, literally what do we mean interior? The same meaning also here. So if a point is an interior point means that lies within the set and the neighborhood of the set also is completely within the same set. Okay, next one is limit point. This is something is relaxed from the interior point definition. See, a point P in R is said to be a limit point for S if for every epsilon greater than 0, P minus epsilon to P plus epsilon contains a point of S other than P. Okay, so here in the previous case we said at least one of the neighborhood is completely contained in S, but for limit point, okay, the condition is every neighborhood. Okay, for the point, whatever neighborhood you take, that neighborhood must contain a point of the set other than P. Okay, P may be or may not be there in the set. Okay, other than P, some other point should be there in the neighborhood and the set. Okay, this is the definition for what? Limit point. Okay, so here one neighborhood completely lying within S. Here every neighborhood must contain a point of S other than P. Okay, the condition if is still relaxed, that point is called what? Adherent point. Adherent point, or otherwise it is also called contact point, right? A point P in R is said to be an adherent point for a set S if for every epsilon greater than 0, the neighborhood P minus epsilon to P plus epsilon contain a point of S. Here just it may contain any point of S that may be P or different from P, that we are not bothered. Just the intersection of the neighborhood and S is non-empty. Look at the difference between limit point and adherent point. For limit point, okay, the intersection must contain a point other than P. Here the intersection may contain point P itself or other than P. Okay, so the condition here is again what? Somehow relaxed. Okay, so here for being an interior point, at least one of the neighborhood should completely lie within S. For these two things, for every neighborhood P minus epsilon to P plus epsilon, here it must contain a point of S other than P. Here every neighborhood must contain a point of S. Okay, so these are the definitions for interior point, limit point and adherent point. And the collection of all interior points of a set is called interior, and the notation is int S or SO. Okay, the another one is the collection of all limit points is called its derived set, and it is denoted by S dash, and the collection of all adherent points is called its closure, and it is denoted by either CLS or S bar. Okay, so these are the notations. So here it is interior, it is derived set, and here it is closure. Okay, next one. The interior of a set is the largest open subset of S. Okay, the interior we said no, it is the largest open subset, and this closure is interior and closure will be something extremely opposite things. Okay, so here what we say, interior of a set is the largest open subset. So what will be the opposite for that one? The closure of a set is the smallest closed superset of S. Here subset, here it is superset, and here it is largest open subset, here it is smallest closed superset. Okay, then next one is a set is open if and only if interior of S is equal to S. That is, a set is is said to be open if, okay, the set is that is all the points of the sets are interior points. Okay, a set is said to be open if all its points are what? Interior points. Otherwise interior of S is equal to S. In the same way here, a set S is said to be closed if and only if closure of S is equal to S. That means every point is a limit point, because here in the next page I will have a relation S bar is equal to S union S dash. Okay, that I will come to it later. So here how do we say a set is open if and only if it all its points are interior points. In the same way, a set is closed if and only if it contains all its limit points, and those are the only limit points. Okay, so closure of S equal to S, then only the set is said to be closed. Next one, the interior of a set is the union of all open subsets of S, and here the closure of a set is the intersection of all closed supersets of S. Okay, right? Then next let's see for some standard sets. See, for interior of empty set is empty, derived set of empty set is empty, and closure of empty set is empty. Okay, and then interior of R is R, and closure of R is also equal to R. I already have uploaded video for each one of the three things separately. There I have given full explanation on how to find all these things. This video is just a consolidation and a comparative study. Okay, so if you want to know in detail about how to find the interior and closure and derived set, you go to the video and you can learn it fully there. Okay, this is just a comparison, so just I am comparing them. Okay, already while studying about open and closed sets, I told you the real line is both open and closed. Okay, so here interior of R is equal to R implies R is open, and closure of R equal to R implies R is closed. Okay, and the same thing here also, empty set is also both open and closed. Okay, both real line and empty set are both open and closed. Okay, and then what about the derived set? R dash equal to R, that is every real number is a limit point for itself. Next, some of the properties. If S is a subset of T, then interior of S is a subset of interior of T. This property is same for all the three. And derived set of S is a subset of derived set of T, and closure of S is a subset of closure of T. Okay, then for intersection, interior of S intersection T equal to interior of S intersection interior of T, and closure of S intersection T is contained in closure of S intersection closure of T. Okay, and then interior of S union T is contained in interior of S union interior of T, and closure of S union T is equal to closure of S union closure of T. So these two things will be reversibly coming here. Okay, and for derived set, we don't have relation for intersection. For union, S union T the whole dash, derived set of S union T equal to derived set of S union derived set of T. And then here for intervals, how to write interior, closure and derived set. Okay, for writing interior, you have to put open brackets, that is open sets, that is any closed interval if they are given, no, just write open brackets. Okay, so interior of closed interval AB equal to open interval AB, and closure of closed interval AB equal to closed interval. So for interior you have to put open brackets, and for closure you have to put what? Closed brackets. That is how you can remember. Okay, and then I will come to derived set later. Then interior of open interval AB is equal to, already it is open, no, so it is equal to the same, and closure of open interval AB is equal to closed. I told you, no, for finding closure just you put closed brackets, that's all. And interior of Q means what? Rational numbers. Rational numbers is equal to empty, but closure of Q is equal to R. And interior of Z is also empty, and closure of Z is equal to Z. Okay, let me come to limit points. For limit points also, derived set of closed interval equal to closed interval, and derived set of open interval is also equal to closed interval. And Q dash is equal to R, that is every real number is a limit point for rational numbers, and Z dash equal to 5. Okay, and then this is one relation which will be helpful for doing problems. Interior of S equal to R minus, that is complement. Okay, R minus closure of R minus S, and closure of S equal to R minus interior of R minus S. Okay, these two will be helpful when you are given with some problems for finding either interior or closure. And if you are not sure, suppose if you know closure but you are not sure about its interior, you can make use of this formula. Similarly, if for a given problem you are familiar with its interior but you are not sure about the closure, means you can make use of this formula. Okay, right? And closure of S equal to S union S dash, that is This formula also you can make use for finding what, for finding closure. Okay, closure of S is simply S union, that is all the points of the set and all the limit points are will become what, adherent points for any given set. And then this is the famous example in limit points, that is 1 by n sequence. This is having only one limit point, namely singleton 0. Okay, this is a very famous example in limit point that you won't forget. Suppose if you want to find the closure for this set, you can make use of this formula. What this formula says, closure is nothing but S union S dash. So the set along with its limit point. What is the only limit point? 0. Okay, and then interior is equal to empty, because see, you can make use of this formula. So interior of this set is, if suppose unknown, then just to find closure of R minus S. This is closure of S, no, find closure of R minus S. R minus this set is what? R only, and then R minus R is empty. So interior of 1 by n with n belong to Z plus is empty. Okay, that's all. If you want to know all the things about closure, derived set and interior of a set, the link is given in the description box. You go through the videos, then you can understand it better. Okay, thank you.